Welcome back to Chapter 6, where we're talking about work and energy. And at the end of the last video, we just introduced potential energy and said that potential energy due to gravity specifically, because there are different forms of potential energy, is equal to mgy, where y is, well, it could be h. The variable might change in certain situations, but is basically the difference in the y direction. So whether we want to call that height or just some arbitrary distance y, or y2 minus y1, it's all representing the same thing, some height above a chosen reference plane. So this reference plane may change depending on the situation. It may be some height above the floor, some height above sea level, some height above just some arbitrary starting point. So potential energy is something that cannot be expressed absolutely, but can be expressed relative to some starting point. So so that's what I was just saying. If potential energy due to gravity is mgy, where do we measure y from? It can be whatever you want it to be. You just need to clearly establish what that starting point is. As I said, it could be the floor level, it could be the top of a table, it could be sea level. No matter what you choose, throughout the solution of the problem, just maintain that consistent reference point. Establish at y equals 0, and then we can describe the change in potential energy. So let's look at an example problem here with a roller coaster car that is going to start at position 1, and then it will go up to the peak of this hill, and then it'll go down that hill to a point down here. So what are we going to call our 0 point? We could say that this is 0, and that would mean that this is 15, and the top of the hill is another 15 or 25. Or we could say that the beginning, starting point 1, is 0, in which case this would be positive 10, and then this would be negative 15. The point I'm trying to make here is that it doesn't really matter. You can establish the rules however you want them to be. It's just that once you do so, stick with it. Be consistent throughout the solution of your problem. In this particular example, our car here, the elevator, or not elevator, but roller coaster car, has a mass of 1,000 kilograms. And we want to find the difference in potential energy between points 2 and 3. So what is the difference between the highest point and the lowest point? So depending on what reference you're going to use, your numbers may look slightly different, but it should still, in the end, result in the same answer. So there are a couple different ways we could go about this. I think the simplest way would be to call the elevation of point 3 down here 0, and then measure up from that 15, and another 10 makes 25. Call that 25, and then we can calculate the potential energy difference between points 2 and 3 all in one step. So the potential energy due to gravity is mgy. The mass of the roller coaster car is 1,000 kilograms. The acceleration due to gravity is 9.8 meters per second squared. And the change in elevation is 25 meters. So let's calculate that. So I got 245,000 joules. But if we look at the problem statement here, we've been given, could be argued one, but I'm going to say two significant figures. So this should really be 250,000 joules. And then to avoid any confusion over whether or not these zeros are significant, we should put this into scientific notation. We could say 2.5 times 10 to the 5th joules is the amount of potential energy that the roller coaster has, the difference between the highest point and the lowest point here. So gravity is not the only thing that can give an object potential energy. We can also store potential energy in a spring. So a spring has a certain distance that it wants to be, that it is in its relaxed state, and we can compress that spring, and that stores up energy in it. When we let it go, the spring wants to be restored to its original length, and so it moves, and in this case pushes this ball with it to the right. So it imparts some of its stored energy into the ball and converts it into kinetic energy. The force required to compress a spring any distance x away from its original length at rest, or to stretch it either way, to compress or stretch, is negative kx. So k is what's called a spring constant. It varies from spring to spring, so every spring will have its own constant. And x is just the distance that we are moving it away from its original starting point. And so this Fs is always wanting to take the spring back to its original position. If you stretch it out to the right, the spring says, nope, 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 I want to go back to the left, which is why this is negative, because this is a restoring force. It wants to go back to its original position. If you compress it to the left, the spring wants to go back to the right. So the F sub s force in the spring is always opposite the direction we push or pull it. And Robert Hooke was the scientist that is most associated with springs. And so this spring constant is also sometimes called Hooke's constant for the spring. Very closely associated with Robert Hooke. So we're going to use this subscript EL to denote elastic potential energy. So potential energy elastic is equal to 1/2 kx squared. Again, k is the spring constant, and x is the distance we have stretched the spring out. So let's take a moment to talk about conservative and non-conservative forces. So gravity is an example of a conservative force. If you were to lift an object up in the air, let's say we had a crate on the ground and you had to lift it up. It wouldn't really matter if you lifted it up in a straight line or if you lifted up in some sort of wavy line. The work being done is entirely based on the height that or distance that you are lifting it. The path taken to achieve that height doesn't affect the amount of work done. However, there are examples where the path does matter. Anything involving friction, for instance, which is a non-conservative force, is going to make the path taken affect the amount of work done. For instance, if we have a crate on the floor here and we want to move it from position 1 over to position 2, you probably would guess that the least amount of work required to get it there would be to move it in a straight line, and you would be correct. If you were to take this wide looping arc to get from point A to point B, you would end up doing more work. But why is that? We're still, the end result is still the same. We've gone from position 1 to position 2. And the reason is because as you push the crate along the floor, friction is working against you. Friction is doing negative work, which you have to do positive work to cancel that out. And the longer you push it along the floor, the more of that friction force you have to overcome. So gravity, lifting things up, elastic, like elastic springs, and electrical forces are conservative. Friction, air resistance, and these other things listed here are examples of non-conservative forces. So with these examples, the path taken does affect the amount of work that needs to be done. Now, I do want to point out that non-conservative forces do give the illusion that the law of conservation of energy is being violated. So the law of conservation of energy says that energy can't be created or destroyed, only changed from one form to another. And friction kind of gives you the illusion or the thought that as you are pushing that crate along the ground, some of the energy you're putting into the system is just disappearing. It's turning into nothing. And that's not the case. The energy is still present. It's just being changed into a different form of energy. If you were to rub your hands together quickly, creating friction between the two of them, you would feel your hands warming up. And so that's what friction does. It changes some of the energy in our system to another form, like heat, that is not really what we are trying to achieve. That's not what we want, but nonetheless, that is what is happening. So non-conservative forces take energy from our system and changes it in a way that is not always desirable. So if we're looking at an example like pushing that box along the ground, the net work of the system is equal to the conservative work that we put into it plus the no, I want to make that a W. There we go. WNC, non-conservative force work that is done. So in the example of pushing the crate, it's like the conservatives are push, and non-conservative is friction, which is going to be a negative work. So we have to do work. Friction is working against us. The sum of that work is the net work done on the system. And the work done by those non-conservative forces can be found by looking at the change in kinetic energy and the change in potential energy of a system. So again, if it kind of almost seems like some energy is disappearing out of our system, it's not disappearing, it's just doing non-conservative work. So non-conservative forces, if we ignore them for now, then we can look at a system, a situation, and say that the total amount of energy in that system is equal to the sum of all of the kinetic energy and the potential energy. And this is leading up to the law of conservation of energy, which I kind of already mentioned in the previous slide. The final energy in a system has to be equal to the initial energy of the system, as long as we ignore those pesky non-conservative forces like friction. So it is constant. It doesn't change. The total amount of energy in the system remains constant. So it looks like I'm coming up pretty close on my 15-minute limit. I'll stop there, and we'll talk more about this conservation of energy in the next video.